Good afternoon all. I'm here to talk about the VVC decoder in FFmpeg. I'm going to introduce VVC. I should imagine if you're in this room you're already somewhat familiar or at least interested, but I'll refresh some of the coding tools and some of the objectives that it has. Talk about where FFVVC, the FFmpeg VVC decoder, fits into that. Again, what new coding tools VVC introduces. Talk a bit about the threading model, which is one of the more interesting things for those of you who already have some experience with FFmpeg. And then go over performance, how that compares to previous codecs and the other VVC decoders out there. And conclude the talk talking a little bit about the Google Summer of Code program this summer and the next steps for FFVVC. First of all, a disclaimer. I did not write very much of this code at all. The credit should go to Noemi in China, who unfortunately couldn't be here today. Who am I? I am Frank Plowman. You can find me at frankplowman.com. There's various other contact details on there. I was one of the Google Summer of Code students this summer working on this project. As you saw in the agenda, we'll talk a little bit more about what that involved later. So yeah, going into the introduction then. So VVC, or not H.265, H.266 that should read, is a new standard from the JVET. It's succeeding H.264 and HEVC, so quite big boots to follow. It's got two main objectives. So it aims to have 50% lower bit rates than HEVC for the same quality of video. And as the name suggests, versatility is the other main objective. So that involves a lot of the new coding tools are for things like screen content coding, adaptive resolution change for things like video teleconferencing, independent sub-pictures. We'll touch a little bit more on that later. But yeah, versatile applications underlie a lot of the decisions made in the design of VVC. The open source landscape for VVC, so for encoders, you have VTM, which is the reference software. You're not really going to want to use that for practical encoding. You have VVenc, which is developed by the Fraunhofer Institute, and that is a practical encoder, very fast. And finally, you have UVG266, which is an open source project developed by the community, though that... And then on the decoder side, you again have VTM, you have the jeweler VVenc, you have VVDEC, which I believe there's a lightning talk on that in a little while, which is very fast, very good decoder. You have also developed by the Fraunhofer Institute. You have OpenVVC, which is a community project VVC decoder, which is relatively performant for single core. Unfortunately, that has now been abandoned. I don't think there's been a commit in about 2 years. And finally, we have what this talk is introducing, FFVVC. So the state of FFVVC, the C code was merged at the start of the year. I believe it was a month ago exactly now. As Jean-Baptiste talked about in his talk a little while ago, we believe it will be in FFmpeg 7.0, but possibly under some sort of experimental flag. The interprediction assembly has just been merged about a week ago. We have some other assembly that has been written and is in the review process. It's important to note, though, that FFVVC is not yet main 10 complete. There are some coding tools that are missing. The big one that we've heard from the community is intra-block copy support is not yet implemented. There is a patch set for that that's in the works. So that should be coming. I'd be doubtful that it'll be in the 7.0 release of FFVVC, though. Most of the other features that are missing are things that are a bit more exotic than intra-block copy. So features such as wraparound for 360-degree video is not yet implemented. Independent sub-pictures, reference picture resizing, some of the more exotic stuff, but that will all come in time. So yeah, this shows the assembly status, what has been written so far, what we're prioritizing, and what we've been able to reuse from HEVC. So things that we've prioritized so far are largely low-hanging fruits. So the interprediction, we were able to reuse quite a lot of that from HEVC for good gain. SAO is entirely identical between HEVC and VVC, so we've been able to rip that directly. Interprediction and ALF are both big contributors to the decode time in C only, so they're high priority. One of the GSOC projects last year was working on the ALF stuff, so we'll talk about that a bit more, so that's on its way. And Inter, we've managed to get some bits out of David for the more generic stuff, just like averaging functions. So that's been effective in getting a quick speed up there. But we need your help with this. There's not many of us working on this at the moment, and there's a lot of assembly to write. And that's going to be key to performance, as we'll see in the performance later on. Decoder size. So FFVVC is, I believe, the biggest decoder now in FFmpeg in terms of lines of C. I'm not sure how it compares to David, but even being the biggest decoder in FFmpeg, it's still much smaller than OpenVVC and VVDC, as you can see here. So how do we manage to achieve that? By being in FFmpeg, basically. We're able to reuse parts from previous codecs. We're able to use the CBS Quebec reader you can see there, and reuse like whole swathes of the code, also parts of the binary, so it's kind of hard to measure that, but you getting more bang for your buck in terms of the size of a compiled libav codec. In the future, I believe we may be able to also use some aspects of hardware decoder APIs to do the DPB reference management. We managed to be much, much smaller, and that's one of the main reasons really motivating putting this inside of FFmpeg. The other one being FFmpeg's vibrant community, we can say, which hopefully will help maintain this into the future. So moving on to what's new in VVC. So there's a lot of new coding tools, like a dizzying amount. You can see here, you could talk for an hour, and many people have, about even a subset of these. As we say, we haven't implemented them all yet, but there's loads more to play with, which feed back to the ability to make much smaller bit streams, and also to make more versatile video content. What FFVVC introduces that's new for FFmpeg is this stage-based thread model. So lots of previous codecs have the frame and slice thread models, which do well for sort of low numbers of cores, but have some sort of hit a ceiling at a certain point. And so FFVVC uses a much more fine-grained thread model, which is able to allocate threads based on the stage of decoding individual CTUs. And yeah, as that says, it means we're able to much better utilize higher core counts. And so our C code, with no assembly, we're able to decode 4K at over 30 FPS on a relatively high-end desktop processor, but I think that's really impressive. This thread model is possible to implement in HEVC. FFHEVC does not use it. I think it's also possible to do stage-based decoding in AV1, but it wasn't a factor in the design of AVC. The way that it works is you divide each CTU into several stages of decoding. They're all listed there. And the key thing is that each stage depends only on the current or previous stage of the neighboring CTUs. And so you can start doing the D block of one stage before you've done the pass, even in the top left corner very far away. Before you've done the inter, I think you have to do the pass for all first. And the effect that you get from this is this sort of wavefront that progresses across the image of each of the different stages, and it allows you to use much more cores. To allocate those cores, we've had to introduce this new AV executor utility, which has been made available in libav-util, so you can use this for other projects inside FFmpeg. It's a really simple algorithm at the moment, but centralizing the control of allocation of threads, not repeating yourself, means we have now one location where we can make improvements here. At the moment, it's a really simple algorithm. It's based on, I think, some of the earlier implementations inside Python and Java's executor structures, or whatever they call them. But yeah, having that one thing in one location that can be used throughout FFmpeg to improve multi-threading. So on to the performance section. So at the moment, it's pretty slow compared to previous codecs. I mean, this is to be expected to a certain extent. VVC is just a more complex codec than previous generation stuff. It has to be in order to achieve high rates of compression. This SIMD here, false and true for FFVVC. So this is with stuff that's not yet in FFmpeg master. This is with the current state on the development staging repo. You can see we are getting about over a doubling of speed increase for FFVVC already, but there's a long way to go, as you can see from David's really impressive assembly speed up they have there. But our multi-threading picture is quite different. So that shows you the effect of doing that stage-based multi-threading. We're just much more easily able to use higher numbers of cores. Note here that this is using hyper-threading, which is why you've got quite the knee there at 6 threads. But below 6 threads, it's really not far off from that ideal. You get a core, you get the same multiplicative increase in the speed up. Comparing it to VVDC then. VVDC uses the same stage-based threading model, so you're getting a very similar performance between FFVVC and VVDC. OpenVVC uses the conventional frame and tile-based multi-threading techniques, so that's quite useful on the left-hand side there, that figure, to compare what is the effect of this new threading model. But you can see, and then on the right-hand side, the single-threaded performance, C only, between FFVVC and VVDC is pretty much on par. VVDC has quite significantly different performance on different operating systems, but the average between the two is pretty much the same. And on 4K, it's a similar picture, but everything just gets slightly more pronounced. OpenVVC is slower. The speed up that we're getting from using more threads matters even more for larger videos, so you can see that effect here. But we're still lacking on the assembly front. So VVDC has a lot of assembly already for quite a few different architectures, and you can see they're really sort of pulling ahead once you enable the assembly there. Theoretically, FFmpeg's VVC decoder should have somewhat of a higher ceiling due to the fact that FFVVC's assembly will be handwritten, whereas VVDC's is using intrinsics, and on some architectures using SIMD anywhere as like a portable SIMD library, which introduces some overhead. So with enough time, hopefully FFVVC can be even faster, but we've got a long way to go to catch up to them at the moment. So just sort of wrapping up to the last couple of things here. So talking about the Google Summer of Code program in 2023. So there was 2 Google Summer of Code students contributing to the VVC decoder this summer, myself and Sean Liu. So I worked on a lot of the stuff that was added in version 2 of VVC. So that includes the support for 12 and 14-bit, which needs the range extension, which changes various things to do with the entropy encoder when you get to higher bit depths. And I've also been working on AVX2 optimizations for the inverse transforms. They all had to be written from scratch in the end. There's not very much that you can share between HEVC and VVC due to the way that the HEVC transforms are written in FFmpeg. And Sean Liu is working on also on assembly transforms for the filters, which some of them are in the process of being upstreamed at the moment, I believe. So yeah, next steps, as I'm sure the performance and what we've been working on has sort of shown, we've got a very solid baseline with the C performance and the multi-threading, but we need lots more assembly in there to be able to compete with existing decoders. So upstreaming what we've already got, implementing more functions with assembly, also more architectures. So ARM is going to be a Google Summer of Code project for this summer, potentially also RISC-V. There's a lot of work on doing RISC-V assembly for FFmpeg at the moment, so we're going to need that in time. polishing off the maintain conformance, so implementing those features that I mentioned were missing earlier, particularly intra-block copy is a high priority. The thread optimization for 32 plus cores, so we may be able to improve the AV executor utility for higher core counts if there's sufficient demand for that. And the GPU-based decoder, so a lot of the stuff in VVC is really well designed, particularly to do with the separation of stages that we saw earlier. It means that it's really well suited to decoding on the GPU. So that's something on the far horizon. Concluding, so FFmpeg now has a VVC decoder. I've introduced that new threading model, showing some of the benefits of that. Talked about the C and multi-threading performance and how that compares with VVDC, and given an update on the status, including the optimized assembly we're currently working on. We need help with this, especially with the assembly. There's just very few of us who are all only working on it in our free time, so progress on that front has been relatively slow. So yeah, patch is welcome. All right, yeah, thank you very much for listening. If anyone's got any questions, I'll be happy to try and answer them as best I can. As I said in that disclaimer, I did not write very much of this code. I just did the bits I've talked about, and then I've worked on doing bug fixes, especially since one thing I forgot to mention, part of why we're going to have to be experimental is OSS fuzz. We've only recently started being fuzzed since we went into FFmpeg master, so we're getting a lot of reports for that at the moment that we're trying to work through before we go into like a normal release. But I'll try and answer any questions as best I can. Yes?
Have you considered trying to use C intrinsics like as a step?
So the question was, have we considered trying to use C intrinsics? Yeah, as a step between having fully C code and having handwritten assembly for everything. It's not the FFmpeg way. FFmpeg, everything is handwritten assembly. I think there's a little bit in libsw scale, I believe, but FFmpeg is in the process of removing that tiny bit of C intrinsics that we still have. So yeah, I mean, we're probably not going to do that just out of... You can go faster with intrinsics, so with handwritten assembly. So if we're trying to get that same performance and even beat VVDC, I think it's the only way to go, really. Okay, if there's no more questions, yeah, thank you very much.